Alright guys, we've been learning to 4006 temperature limitations of our terminations, so let's get at it. Keep in mind the previous videos were on 4004. 4004 is huge! Look at all the stuff to do with 4004. We've just covered a small portion of the rules in 4004. We'll come back to these guys in time. We got to do conduit fill, we got to do sizing of bonds, we got to do like box fill and stuff like that. So we'll cover all that stuff, and then we'll come back to a number of other rules here in 4004. Okay, 4006 covers temperature limitations. Keep in mind that there are other rules within Appendix B, but let's read through this. Where equipment is marked with a maximum conductor termination temperature, the minimum size of conductor used shall be based on the ampacities of tables 1 to 4, with all relevant correction factors being applied as required by 4004, which is what we've been doing, right? We've been looking at free air, cable, conduit, copper, aluminum, looking at tables 1 through 4, and then using, and so far we've been only using tables 5A and 5C for ambient temperature and more than 3 conductors in the conduit. But this rule, 4006, tells us that the temperature column that we're looking at in tables 1 through 4 has to keep in mind that it has to correspond to the maximum termination temperature marked on the equipment. So let's take a look at these breakers here. Let's zoom in a little bit. So with these guys, you can see that, I don't know if you can make it out here, that this breaker right here is only good for 75 degrees. Right, so these terminals here on line and load side of our breaker are only good for 75 degrees. So it doesn't matter if that we fed it with a 90-degree conductor. This is now going to take precedent when looking at which column in tables 1 through 4 we're going to make use of. Right? Take a look at this 100 amp breaker here. This guy is good for copper or aluminum, being 60 degrees or 75 degrees. It's highly unlikely that you're going to find terminations that are actually good for 90 degrees. So most of the time we're going to be using the 75 degree column from now on when we're looking at ampacity of our conductors. Okay, it doesn't matter you're using a T90 or RW90. If the terminations are only good for 75 degrees, you have to make use of the 75 degree column in tables 1 through 4. Okay, that's based off 4006, subrule 1. Let's take a look at the other rule here, subrule 2. So if it's not marked, let's look at subrule 2A first. So if you are using a load that's rated not more than 100 amps, or you're using it marked for use with number 1 AWG or smaller, and the equipment isn't marked on the temperature limitations of the terminations, you're going to have to go with the lower value of 60 degrees for those terminations. Most of the time, like in this case, they're clearly marked as to what the temperature actually is on the terminations. If it's not marked, and you're using something that less than 100 amps or number 1 AWG or smaller, you're going to have to go with the 60 degree column. Okay, if you're going with higher currents, so if we're looking at rated at more than 100 amps or marked for use with a conductor larger than number 1, well then you can make use of the 75 degree column. That's super frustrating when it highlights the wrong thing. So more than 100 amps, or you're using a conductor larger than number 1, and the equipment is clearly not marked as to what the temperature rating is of the terminations, you're going to have to go with 75 degrees. Okay, so less than 100 amps and smaller than number 1, 60 degrees. More than 100 amps and conductors larger than number 1, 75 degrees. Okay, so hopefully those are making sense. We're going to do a couple examples with those guys. Let's look at the other rule here, subrule 4, and this determines why we've said, made that note on our previous examples that we're looking at the max ampacity of the conductors, but it's not really real life, right? And we made note that that the conductors were not within the first 1.2 meters of conductor length measured from the point of termination on the equipment to this point on the conductor. So that's just meaning that if you're going to terminate the cable to a breaker or a disconnect or something like that, and it's only good for 75 degrees, well, that heat is going to transfer for a long distance on the conductor. Right? So we want to make sure that within the first 1.2 meters that we've derated that conductor based on the 75-degree column. After the 1.2, we can put a junction box and we can make use of the 90-degree rating on the insulation if we're using T90 or RW90 or something like that. And then going to the load, we would have to put another junction box and then drop down to, possibly drop down to or go up to a larger conductor size because of drop down to the 75-degree column, but that would mean that we're going up in conductor size. Right, so the 1.2 meters is going to be seen in this next example. So let me bring that up right now. Okay, so with most of the examples that I'm going to give you, I'm going to show the question and then I'm going to show the answers. In this case, I'm showing everything all at once. So with the previous examples, we were looking at the conductors right here. Right, we're saying that they're not within 1.2 meters of the equipment. So in all the previous examples, we were making use of the 90-degree column if we're using a 90-degree insulation. Now we know that we can't do that, right? If we're within 1.2 meters, we have to go with the lower rating being 75 degrees on our termination temperature rating. Okay, so in this example, we're going to look at, what size conductor between here and 1.2 meters, so from here to this junction box, do we need to use for 125 amp load? Then can we go down to a smaller conductor from this junction box to this junction box? So say we got discussing long run, right? We want to, reduce our cost. So we're going to try and go with a lower gauge of wire. So we could possibly do that and make use of the 90-degree column on table 2, right? We got copper conductors and conduits. We're in table 2. So we might be able to go down to a smaller conductor size. But then when we go from this junction box to, in this case, the panel board, which is drawing 125 amps, then we're going to have to possibly go back up to the same conductor size that we had right here. So it doesn't happen all the time, but this is one example where you would be able to reduce your conductor size and by making use of the 90-degree column because you're 1.2 meters away from the equipment. Right? The heat on here is not going to transfer to the equipment. We're far enough away. Okay, so that's making use of this rule here, 4006, sub-rule 4. Okay, so the question is find the max ampacity of the copper conductors wire required from the panel to the junction box using the 75-degree rating, and between the junction boxes using the 90-degree rating. So we're copper, we're an EMT conduit, so we're in table 2. So let's go to table 2 and take a look. Okay, so in the first case, we're in the 75-degree column. We need a conductor that's going to handle 125 amps. Now, in all these examples, I'm still talking about non-continuous loads. We're going to get to continuous loads in the next videos. So it looks like in the 75-degree column, so from here to this junction box, I need a conductor that's going to be able to handle 125 amps. So it looks like I'll be good with the number 1 AWG. Okay, from this junction box to this one, we've got a much longer run. We want to see if we can reduce our conductor size. So we're going to make use of the 90-degree column. So looking in the 90-degree column, again, we're looking for something that's going to handle 125 amps. And it does look like we can reduce our conductor size down to a number 2 AWG. Okay, so in certain instances, you can make use of the rule 4006, sub-rule 4, in order to reduce your conductor size. Most of the time, we're just going to run a conductor from here straight to here, but because we're making use of the 75-degree column, we may have to use a larger conductor for the entire run. Okay, so this doesn't happen all the time. I made a note here that if we were looking for 100 amps, then both would be a number 3. Let's take a look at that. So first of all, let's take a look at the 75-degree column. We're looking for 100 amps. Again, non-continuous load. So 100 amps, looks like we're going to be using a number 3 from here to this junction box. Can we get away with a smaller conductor size once we're 1.2 meters away? Using the 90-degree column, well, let's see, with 90-degree column here, coming down, we need 100 amps. It looks like a number 4 is not going to cut it. Number 4 is only good for 95 amps. So in this case, the entire run, regardless of the fact that I'm using 90-degree conductors and I'm 1.2 meters away, I'm still going to have to use a number 3 for the entire run there. So in some instances, like the previous one, where we're looking at 125 amps, yeah, we can go from a number 1 down to a number 2. But in this case, if we're 100 amps, it's number 3 all the way. Okay, so hopefully this is making sense, guys, in why I was alluding to the fact that we've got to make use of the temperature rating of the terminations. And from now on, it's probably going to be 60 or 75 degrees. It is highly, highly unlikely that you're going to see some type of breaker or termination that has a 90-degree temperature rating. Okay, guys, let's take a look at a couple other examples here. Okay, example number 17, guys. So in this example, we're going to have more than 3 conductors in the raceway, and we're going to have an ambient temperature above 30 degrees. And we're also going to make use of the fact, or keep in mind, that our termination temperature rating is 75 degrees. So even though we are running a T90 insulation, we're going to have to make use of the 75-degree column in table 2, right? Because table 2, we got EMT and we got copper conductors. Okay, so let's find the answers below. Okay, you can stop the video here, see if you can find the answer to this question, and then restart the video, and then I'll show you the answers. Okay, so first step, as always, is it copper or aluminum? It's copper. Is it free air or raceway or cable? It's raceway. It's EMT conduits. We're in table 2. Then we've got to use the lower temperature rating of the insulation versus the temperature rating of the termination, right? That's 4006 sub row 1. So in that case, we're in the 75-degree column here. So let's highlight that guy. And it looks like we have number 10s, right? So number 10s are good for 35 amps. And we got number 12s. So the number 12s are good for 25 amps. Okay, so those are our base ampacities. If we only had 3 conductors in the pipe, which we don't, we have 18. And if we were below 30 degrees, which we're not. Our expected ambient temperature is 35 degrees. Now again, as we alluded to in the previous videos, it doesn't matter if you go to 5A first or 5C. I've just decided to go to 5C first. Okay, so we have base ampacities of 35 and 25 amps from table 2. Now we're going to have to go to table 5C, which is based on 4004 subrule 1C. And if we go to 5C, how many we got? 18 conductors, right? So 5C, 18 conductors, looks like we're doing 70% of that base ampacity. So 35 amps times 0.7. Now the number 10s are only good for 24.5 amps. Number 12s, we're good for 25 amps. Then now we're going to get 70% of that ampacity. They're only good for 17.5 amps. Not only do we have too many, like more than 3 conductors, 18 conductors in the pipe, which means that a couple things. There's not enough area, surface area for the conductors to dissipate their heat. And now we've got the magnetic field of one conductor cutting across the other conductor, inducing counter EMF for XL inductive reactance onto that conductor. So a number of reasons why we had to make use of table 5C there. Okay. In addition to that, we have also got an ambient temperature that's greater than 30 degrees. So now, obviously, the conductors can't dissipate their heat because it's too hot. So now we're going to table 5A based off 4004 subrule 7B1. So let's go to 5A, guys. We were using the 75-degree insulation rating. It looks like our maximum expected ambient temperature is going to be 35. So now we're looking at 94% of the ampacity that we found from table 5C. So now we've got the 24.5 amps that we had for the number 10s times 0.94. Those number 10s are now only good for 23.03 amps. Then number 12s, we're good for 17.5. Now we've got 94% of that. The number 12s are now only good for 16.45 amps. Okay, so later on we're going to look at what our load is and then determine what the conductor size is for those loads. But in this case, we're just looking at max ampacity of the conductors. Okay, if these values were too low, then we'd obviously have to upsize our conductors in order to accommodate the 0.7 and the 0.94 reduction in values. Okay, so hopefully everything makes sense so far. Same steps as we had before. The only thing we're keeping in mind is that it's highly unlikely that you're going to be making use of the 90-degree column in tables 1 through 4. Okay, let's take a look at the next example, guys. And let me know, like in the comment section, if this is working for you, like where I show the question and then show the answers. I'm not drawing anything out. I'm just clearly going through the steps here. There's other videos where they're drawing out values on the screen. if that works for you better, or that's, you find you're understanding it better that way, then let me know. I just decided to go with this style, but if it's not working for you, I need to know right away. I also need to know whether the volume is good as well. So let me know if volume and pace of the video is matching with your learning style and your equipment. Okay, let's go on to the next example, guys. Okay, guys, example number 18. So keep in mind that these guys are all non-continuous loads. We're going to get to continuous loads in subsequent videos. Okay, so in this case, we've got termination temperature ratings lower than the conductor insulation temperature ratings. Okay, so I'm telling you what we're doing in the top here, but when it gets to questions, you're going to have to keep all of this in mind, right? I'm not going to give you these hints on any of the questions there. Okay, so find the max ampacity of each of the copper conductors required from the panel to the given load. Okay, in all of these examples, I'm just going to use EMT conduit just to keep these things simple, and I'm going to use copper conductors. So in this case, we have 120 240 volt single phase panel. Keep in mind that the termination temperature rating on this guy is 75 degrees. We're going to run T90s from the panel to this load. This load is a 120 240 volt single phase load, and it's drawing 45 amps, and it also has termination temperature rating of 75 degrees. Keep in mind, it doesn't matter whether we're looking at this temperature rating or this temperature rating or this temperature rating. Whichever one is the lowest is going to determine which column we're going to be looking at in table 2. Okay, this guy is a single phase load. It's 120 240 volts. Keep in mind that the neutral does not count for ampacity, right? The neutral is carrying the unbalanced load. So it's not carrying the full load that your current carrying conductors would be carrying. So here we'd be pulling 3 conductors, 2 hots and a neutral, but in this case, there's only 2 current carrying conductors. Okay, I made a note that ambient temperature is expected to be below 30 degrees, and we're doing non-continuous load, so we don't have to worry about the 80% rule at this point. Okay, stop the video here, see if you can find the values for these guys, and then I'll bring up the answers. Okay, guys, so obviously we're going to table 2 because we got copper conductors in conduit. We're going to use the lower temperature rating for using table 2. That's 4006 sub rule 1 to find the gauge of wire required for the given load. We've made a note that neutral counts for conduit fill, but in terms of derating with table 5C, it does not count as a current carrying conductor. So with this one, super simple. We're just going to table 2. We're in the 75 degree column, so let's highlight that. And we've got a load at 45 amps, non-continuous load. So we're scrolling down here until we see a value that's 45 amps or greater. And it looks like for this example, we're going to have to pull a number 8 conductor. Right? So we got 2 number 8 conductors. I would pull a number 8 for the neutral. The neutral can sometimes be smaller than your current carrying conductors, but I would just pull the same size of neutral there. Okay, so we got 2 hots of number 8s and a neutral at number 8 as well. Okay, that number 8 is good for 50 amps. It's definitely going to handle the 45 amps that this single phase load is going to be pulling. Okay, guys, let's take a look at the next example. Example number 19. Again, termination temperature ratings are going to be lower than the conductor insulation rating. So now we've got a 3-phase panel, 120 208. Termination temperature rating here is 75 degrees. We are pulling conductors to a 208 3-phase load that's going to be drawing 77 amps. It's a non-continuous load, so we don't have to make use of the 80 degree rule. Termination temperature ratings on the load are also 75 degrees. Ambient temperature is going to be below 30 degrees, so we don't have to worry about tables 5A. And with this guy, we only have 3 conductors in the pipe, so we don't have to make use of 5C either. We're just going to be going to table 2. Table 2 because we have copper conductors in a conduit. Okay, doesn't matter that we're pulling RW90s. 4006 sub rule 1 says that we have to make use of the 75 degree column because of the temperature limitations on our terminations there. Okay, so we got 77 amps that we're looking for. Okay, stop the video here, see if you can find the gauge of wire that corresponds to this, and then I'll show you the answer. Okay, so again, table 2, copper conductors in conduit, using the lower temperature rating being 75. So again, we're in the 75 degree column here of table 2. And we're scrolling down, we need to find a value that's 77 amps. Careful here when you have values that are very close, right? Temperature termination rating and the amperage are very close. So careful when you're looking for your current value. We're looking for a current value of 77 amps. So we're coming down for finding a value that's 77 or greater. Looks like 85 amps is the value that we're going to make use of. We can't make use of number 6 because number 6 is only good for 65 amps. So it looks like we're going to be pulling number 4 conductors, right? It's a 3-phase load drawing 77 amps. We need line 1, line 2, and line 3. So we're going to bring 3 number 4 conductors. Those number 4 conductors are going to be good for 85 amps. So they can definitely handle the non-continuous load of 77 amps being asked there. Okay, so hopefully you're getting the gist of this. We've done a number of these examples here, and now you're keeping track of the fact that it's highly unlikely that we're going to be making use of the 90-degree column there. Okay, let's look at another example. Okay, next example, guys. We're back to single-phase panel. That panel has a 75-degree temperature rating on the terminations. Looks like our loads also have 75-degree temperature ratings on the terminations here. We have 122 40-volt single-phase panel running EMT conduit. Like I said, everything's going to be EMT. Everything's going to be copper. So I haven't mentioned copper here, but I have mentioned it here. We're going to pull RW90 XLP unjacketed conductors over to this junction box, and then we're going to split up the conductors. Some conductors are going to go here. So we're going to have 2 wires going to this 40 amp load. And then we're going to have 3 wires going to this 122 40-volt 60 amp load here. Those guys are 2 current carrying conductors, right? Even though it's a 122 40-volt load, remember that the neutral does not count for ampacity. Okay, so in terms of current carrying conductors, 2 wires here and 2 wires here. Okay, let's find the ampacity here. Stop the video and then restart once you're done, and I'll show you the answers. Again, we're going to look at the conductors here, and then we may be able to derate or we may be able to go down to smaller sizes here. We'll see, right? Because in this case, we've got 4 current carrying conductors. So we're probably going to have to make use of, we're definitely going to have to make use of 5C. Okay, guys, let's find the answer for this one. So we got copper conductors in a raceway. So we're going to go to table 2. We got 75-degree terminations here. So both at the panel and at the loads. So we're going to this column right here. Okay, and let's see, we got 40 amp non-continuous loads here. So we're going to scroll down and find a value for 40 amps. The number 10s are not going to cut it. Number 10s are only good for 35. So our 40 amp loads are going to have to be number 8s. Those number 8s are good for 50 amps. So we got 2 number 8s being drawn into the pipe for our 50 amp 240 volt load. For our 40 amp 240 volt load. And then we've got a 60 amp 122 40 volt load. So going down for 60 amps, number 8's not going to cut it. Looks like we're going to have to go with a number 6 for our 60 amp load there. Okay, so we got 2 number 8s and 2 number 6s here. Okay, and again, we said the neutral counts for conduit fill, but in terms of derating in table 5C, it does not count. Okay, so that's our base ampacity, 50 amps and 65 amps, but we got 4 conductors in there, right? So we got to make use of table 5C based off 40041C. Okay, so if we go to table 5C, we are at 4 conductors. So then we're 80% of our base ampacity there. So the 40 amps that we had there, the 50 amps that we had times 0.8 is going to give us 40 amps max. So that's good, right? That's going to match with the current that was required by the load. So we're still good there. Number 6s, if we take the 65 amps from here and multiply it by 0.8 from table 5C, we only get 52 amps now max for those number 6s. Those number 6s were supposed to be used for the 60 amp load, so we can't use the number 6s. We're going to have to go up by probably 1 size, right? So let's take a look at table 2. Let's erase what we have here. And we're looking for a value that's going to handle the 60 amps, but with the 0.8 reduction factor from table 5C, right? So if we take the next guy, so the number 6 was not cutting it. Let's see if number 4 is going to do it. So number 4 is good for 85 amps. 85 times 0.8, beauty, is good for 68 amps. That number 4, with the reduction factor, because there's 4 conductors in the pipe, is definitely going to be able to handle the 60 amp load now. So in this portion of our piping, we're going to have to pull number 4s for a 122 40 volt load, and number 8s for a 40 amp 240 volt load. Okay, another way to come to the same conclusion, if that didn't work for you, then you can take your 40 amps and your 60 amps, divide it by 0.8, right? That gives you 50 amps and 75 amps. And now you're looking for conductors in the 75 degree column that are going to match with those values. Okay, so if we're looking for 50 amps, looks like 50 amps, well, that's going to be a number 8, right? So that works for this guy right here. And if we take our 60 amp load divided by 0.8, reduction factor, we actually need a conductor that's going to be able to have a base ampacity of 75 amps or greater. And if we scroll down here, that would mean that we're going to have to pull a number 4 in this portion of the pipe where there's 4 conductors. Once we get to this portion and this guy, well, this can continue on as a number 8, obviously. And from here down to our 60 amp load, we could pull number 6s, because in that case, we've only got 2 current carrying conductors. We no longer have to make use of table 5C there. Okay, so hopefully that helps in that now we've got an example where we've got a junction box, we've got loads that are now splitting up from that junction box, 4 conductors in this pipe, 2 current carrying conductors in this one, 2 in this one. So in this portion of our piping system, we had to derate and use a larger size conductor in order to accommodate our 60 amp load. All right, guys, let's take a look at the next example. Okay, example number 21, again, covering non-continuous load ampacity calculations. In this case, there's going to be more than 3 conductors in probably this portion of the pipe. So what do we got? We got 122/8 3-phase panel now. Termination temperature reading on the panel is 75 degrees. So even though we're using T90s, 4006 sub-rule 1 says we have to use a 75 degree column in table 2. Why table 2? Because it's copper conductors in conduit. Okay, we're feeding a 20 amp non-continuous load, 75 degree termination temperature, 2/8 single phase. So that's going to be 2 wires going out to that load, right? 2 current carrying conductors. Over here we have a 30 amp non-continuous load, 2/8 3-phase. So we need 3 wires for line 1, line 2, line 3. And again, the termination temperature reading is 75 degrees. Okay, so 20 amp and 30 amp loads, 2 wires here and 3 wires, so 5 wires in this portion. 5 wires here, 2 wires here, 3 wires here. So in this portion, we're going to have to make use of 5C. I've also made a note here that this is a commercial installation. So even though you can get away with a number 14, minimum gauge on commercial installations is always number 12. Okay, and these guys are copper conductors. So we're going to find the ampacity for copper conductors going from the panel to the junction box, and then from the junction box on from there. Okay, pause the video here and then find the answers. Okay, here we go, guys. So obviously we're going to table 2 because we're copper in a Raceway EMT conduit. So we're in table 2. This is now going to be the value that we're going to be making use of, even though we're using T90s. So again, we're in the 75 degree column here. Right? It's just repetition, guys. Repetition after repetition, then you'll get it. Looks like we're going for a 20 amp load, non-continuous load. So we're going down. Look, their number 14 is good for 20 amps, but it's a commercial installation, so I'm not going to run a number 14. Okay, if I was doing a residential installation, sure, I could run number 14s. This is a commercial installation, so I'm going to run number 12s. Those number 12s are going to be good for 25 amps. Definitely going to handle the 20 amp load that we have here. Okay, then we've got a 30 amp load here. So for 30 amps, we've got, looks like number 10s. Right, so we can look at number 10s here. They're good for 35 amps, so they'll definitely handle the 30 amp load. Base ampacity, if we only had 3 conductors in the pipe, but in this case we got 2 plus 3. We got 5 wires in this pipe, so in this portion from the panel to this JB, we're going to have to make use of table 5C based off rule of 4004 1C. Okay, you'll see that I keep mentioning rules and stuff like that. I find that if you keep mentioning things over and over and over, then it's going to stick. So you'll learn how to go through the question, but you'll also know the rule that you can refer back to later on. Okay, so we got 4 to 6 conductors. So let's go to table 5C. Still have that highlighted. So we're 80% of our base ampacity there. 25 amps times 0.8 gives us 20 amps for the number 12s. So that's good. We're still good with those guys, right? The number 10s, that 35 amps that we had initially is now reduced down to 80%. It's only good for 28 amps. Okay, so at that point, the number 10s are not large enough to feed that 30 amp load when pulled in this portion of our piping system. Okay, so let's go back to table 2. We got to go for the next, probably next size up, right? So most likely number 8s. Let's take a look, guys. So we need something that is going to be providing us with that higher ampacity, so 50 amps, right? We also have to multiply that 50 amps times 0.8, and 50 times 0.8 is going to provide us with 40 amps of ampacity. Perfect for this 30 amp load here. So in this portion of our piping system, the 30 amp load is going to have to be run with number 8s. Once we get to the junction box, then we can reduce down to number 10s because the number 10s are good for 35 amps. And then in this portion of our piping system, we only have 3 wires, so 5C doesn't come into play there. Okay. The other way that we can do this, if you don't want to go through these steps, is you go to table 5C, you know that there's 5 conductors, right? You know that the multiplier is 0.8, and you're going to take your 20 amps that you're looking for, divide by 0.8 gives us 25 amps, right? We're looking for a conductor that provides us with 25 amps in the 75-degree column there. So in that case, we're going to be running number 12s. And we've got 30 amp load. We have to divide that by 0.8. So we need a conductor that's going to be able to provide us 37.5 amps because we're going to reduce that down to 80% of that. So 37.5 times 0.8, we're going to be making use of the number 8s for that load there. Okay, keeping in mind that past the junction box, this can continue on as number 12, and the number 8s that we pulled here can then be reduced down to number 10s to our load there. All right, guys, hopefully everything's making sense. Let's do a couple more examples before we finish off the video. Okay, guys, 3 more examples here. So example number 22, again, non-continuous load. And for this example, we're going to have an ambient temperature above 30 degrees. So what do we got? We got a 122.8 3-phase panel. Termination temperature ratings are 75 degrees C, same as all the others. We're going to run this in PVC conduit. We're going to run RW75 conductors, and it's going to be going outside. 3 conductors. Why 3 conductors? Oh, because we have a 3-phase load that's pulling 40 amps, and the termination temperature rating on the load is also 75 degrees. That load is non-continuous, so we don't have to make use of the 80% rule at this point, but we do have to keep in mind that ambient temperature could reach up to 55 degrees Celsius. So we've got 3 conductors in the pipe, guys. Looks like temperature rating of the terminations and our insulation are identical, so we're definitely going to be in the 75-degree column of table 2. Let's pause here, guys. You guys find the answer, and then I'll bring it up. Okay, so we're copper. We're in a free air Raceway or cable, obviously in PVC conduit, so we're going to table 2 as usual. Table 2, we're in the 75-degree column, and we need something that's going to be able to handle 40 amps. So let's see, we're in 75-degree column of table 2. We need something that's going to handle 40 amps. So going down, the number 10 is not going to cut it. Number 8s look like what we're going to have to pull, right? So number 8s are good for 50 amps. If we didn't have to deal with this, the fact that we have temperature way above 30 degrees. Okay, so now we're going to have to go to table 5A based off of rule 4004, sub-rule 7BI. Okay, or 7B1. Okay, so let's look at 5A. So we had 50 amps. If we're going to 5A, we're using 75 degrees for our insulation. We're up to 55 degrees, smoking hot. So we're only going to get 67% of the base ampacity there. Okay, so for that guy, again, we didn't have more than 3 conductors because we just have 3-phase load, right? 2.8, and even if it was 122.8, the neutral would not count. So we have 3 conductors, no use for 5C. So we went to 5A, went to the 55 degrees ambient temperature and the 75-degree insulation, and now we're at 67% of our base ampacity of 50 amps. So 50 amps times 0.67 gives us 33.5 amps. Well, that's not going to cut it for a 40 amp load, so we're going to have to go to the next size up, right? So next size up, if we go back to table 2, next size up would be 65 amps for number 6. And if we take 65 amps times 0.67, 0.67 again from table 5A, gives us 43.55 amps, which is definitely going to handle the 40 amp load that we have here. Okay, so it looks like final answer there is that we're going to have to be running, in this case, because of the excessive heat that's going to be happening on our conductors that are run in the outdoor installation, we're going to have to run number 6s instead of number 8s to accommodate that increase in ambient temperature there. Okay, other way to do this, again, is to go straight to table 5A. So straight to 5A, knowing that you're in the 75 degree column, knowing that you have 55 degree ambient temperature, that your derating is going to be 67%, and you need, let's go back to table 2. In that case, you've got 40 amps for the load, right, divided by the 0.67. So you need to have a conductor with a base ampacity of 59.7 amps or greater, right, to match with that ampacity required to meet the 0.67 correction factor. So we need 59.7. So scrolling down here, number 8s are definitely not going to do it. So that's where we can get the number 6s right away, in that we have 65 amps times 0.67 gives us 43.55 amps max. Definitely ample enough to cover that 40 amp load. Okay, hopefully everybody's doing well with these guys and you're getting a good feeling on tables 1 through 4 and tables 5A and 5C. And now, dealing with non-continuous load so far, the 75 degree termination temperatures. Okay, 2 more examples, guys. Okay, guys, example number 23. This one we've got unknown temperature limitations on the terminations. So now we're looking at finding the ampacity for a 6.3 NMD90 copper 300 volt rating that's being used to feed a non-continuous 50 amp disconnect. Note the temperature reading of the disconnect terminals is unknown. So we're at 50 amps. The temperature rating of the disconnect terminals is unknown. So now we're at 4006. And which sub row are we on? We're here, right? Because we're at something that's rated not more than 100 amps. So in this case, we're going to have to make use of the 60 degrees column in table 2, right? Because table 2, we're still making use of a cable assembly here, and we've got 3 conductors in the cable assembly. So 3 conductors, and the conductor size is number 6. Okay, so we're going to find the ampacity for those number 6s, and we're going to look at the 60 degree column in table 2. Okay, find the answer and then I'll bring it up. Okay, so let's go to table 2, guys. Right, because we're in table 2 because we've got a 3 conductor cable there, and so we're going to be making use of this row 4006 2A. We're in the 60 degree column, so let's highlight that. Okay, and we pulled number 6s, right? So the number 6 is now good for 55 amps there. Okay, so if 90% of the time the termination temperature rating is going to be there. It's in really small font, so look for it. It's same as the ampere interrupting rating. It's really, really small, but it's most likely going to be there. In this case, it wasn't on the equipment. We're using an amperage that's below 100 amps, and so we're going to make use of the 60 degree column there. So our number 6s in this case are good for 55 amps. Okay, one more example, guys. Unknown temperature limitations. We got to do one with the 75 degree rating, so let's do that next. Okay, guys, next example and final example, number 24, unknown temperature limitations of terminations. Find the ampacity for 3 4-aught RW90 copper 600 volt rated conductors run an EMT conduit that are being used to feed a non-continuous 225 amp load, noting that the temperature reading of the load terminals is unknown. Okay, so now we're above 100 amps, right? So we're still on 4006 temperature limitations, but when the temperature for the equipment is not marked, right? Temperature for the equipment is not marked. Maximum conductor termination temperature shall be considered to be 75 degrees. That's super frustrating when it highlights the wrong thing. Let me see if I can highlight the right thing here. 75 degrees for equipment rated at more than 100 amps or marked for use with conductors larger than number 1. Okay, so we're going to use the 75 degree column, and we're going to make use of table 2 because we're copper and EMT. Okay, find that amperage, guys, and then we'll finish off. Okay guys, so we're going to table 2 because we're copper in EMT. We are now in the 75-degree column, so unknown markings, but we're above 100 amps, right? It's a non-continuous 225 amp load. There's only 3 conductors, so we don't have to make use of table 5C. We're just making use of table 2. And so we're scrolling down until we find, what do we pull? 4-aughts. So we're going down to 4-aught conductors, and the 4-aughts are good in the 75-degree column for a maximum of 230 amps. Okay guys, hopefully everything's working out. Leave me some comments in the bottom telling me, pace, whether you like the way that I'm presenting the material, whether you think it's good volume and stuff like that, whether you like this rather than drawing on the screen, and whether you can see everything and follow me properly. Okay guys, we'll see you guys on the next video. Thanks very much for watching right to the end. Okay, example number 23 here, guys. Why does this not have? Why does this not have that? Okay, guys, example number 23. This one we've got unknown temperature limitations on the terminations. So now we're looking at finding the ampacity for a 6.3 NMD90 copper 300 volt rating that's being used to feed a non-continuous 50 amp disconnect. Note the temperature reading of the disconnect terminals is unknown. So we're at 50 amps. The temperature reading of the disconnect terminals is unknown. So now we're at 4006. And which sub roll are we on? We're here, right? Because we're at something that's rated not more than 100 amps. So in this case, we're going to have to make use of the 60 degrees column in table 2, right? Because table 2, we're still making use of a cable assembly here, and we got 3 conductors in the cable assembly. So 3 conductors, and the conductor size is number 6. Okay, so we're going to find the ampacity for those number 6s. and we're going to look at the 60-degree column in table 2. Okay, find the answer and then I'll bring it up. Okay, so let's go to table 2, guys. Right, because we're in table 2 because we've got a 3-conductor cable there, and so we're going to be making use of this rule 4006 2A. We're in the 60-degree column, so let's highlight that. Okay, and we pulled number 6s, right? So the number 6 is now good for 55 amps there. Okay, so if 90% of the time the termination temperature rating is going to be there. It's in really small font, so look for it. It's same as the ampere interrupting rating. It's really, really small, but it's most likely going to be there. In this case, it wasn't on the equipment. We're using an amperage that's below 100 amps, and so we're going to make use of the 60-degree column there. So our number 6s in this case are good for 55 amps. Okay, one more example, guys. Unknown temperature limitations. We got to do one with the 75-degree rating, so let's do that next. Okay, guys, next example and final example, number 24, unknown temperature limitations of terminations. Find the ampacity for 3 4-aught RW90 copper 600 volt rated conductors run an EMT conduit that are being used to feed a non-continuous 225 amp load, noting that the temperature rating of the load terminals is unknown. Okay, so now we're above 100 amps, right? So we're still in 4006 temperature limitations, but when the temperature for the equipment is not marked, right? Temperature for the equipment is not marked. Maximum conductor termination temperature shall be considered to be 75 degrees. That's super frustrating when it highlights the wrong thing. Let me see if I can highlight the right thing here. 75 degrees for equipment rated at more than 100 amps or marked for use with conductors larger than number 1. Okay, so we're going to use the 75-degree column, and we're going to make use of table 2 because we're copper in EMT. Okay, find that amperage, guys, and then we'll finish off. Okay, guys, so we're going to table 2 because we're copper in EMT. We are now in the 75-degree column, so unknown markings, but we're above 100 amps, right? It's a non-continuous 225 amp load. There's only 3 conductors, so we don't have to make use of table 5C. We're just making use of table 2. And so we're scrolling down until we find, what do we pull? 4-aughts. So we're going down to 4-aught conductors, and the 4-aughts are good in the 75-degree column for a maximum of 230 amps. Okay, guys, hopefully everything's working out. Leave me some comments in the bottom telling me, pace, whether you like the way that I'm presenting the material, whether you think it's, good volume and stuff like that, whether you like this rather than, drawing on the screen, and whether you can see everything and follow me properly. Okay, guys, we'll see you guys on the next video. Thanks very much for watching right to the end.